Hi, everyone. Thanks to the organizers for the invitation. It's really a pleasure to be here and to start this conference. My goal in this mini-course is, or at least for the first part of it, very broadly, is that I want to motivate and discuss the relationship between Anosov, or even pseudo-Anosov, flows on three manifolds, all to be defined. I don't assume you know anything, and which come with invariant foliations. Called stable and unstable foliation. And a picture used first very productively in work of Thierry Barbot and Sergio Fenley that translates this data into a discrete group acting on the plane. Again, now with invariant one-dimensional instead of two-dimensional foliations. And a beautiful picture that sort of translates back and forth between dynamics of flows in dimension 3 and discrete groups actions in dimension 2. And eventually we'll get to some recent work, hopefully, that I've done with a bunch of people, including Thomas Barthelmé, Christian Bonatti, Sergio Fenley, and Stephen Frankel. Okay. But we're a diverse group here, and it's Monday morning at 9 o'clock, so I assume I'm starting from 0, although I will accelerate quickly, so watch out. So to start from first principles here, the idea I want to get across is how you might get some foliations out of hyperbolic dynamics. Okay, so let's do this by example. I will take a matrix with two different eigenvalues. Actually, a matrix in SL2Z. Let's take 2, 1, 1, 1 to be very concrete. It's a linear map. It acts on R2, but I put it in SL2Z so it preserves the integer lattice. So this descends to act on the R2 mod Z2, the torus. And this particular matrix has two eigenvalues off the unit circle. One is, expanding. One is bigger than 1. One is less than 1. So if I draw a picture of, here's the plane. And here's a fundamental domain for the torus. There's two invariant directions, the eigendirections for this map. Wow, that blue looks like white, but that's okay. One which is contracted under iteration. If I take 2 points that are on this contracting eigendirection and I iterate the map, they get closer and closer together as they go around. And then I have transverse to this an expanding eigendirection. Different leaves of this foliation are permuted, but the direction is preserved by the map. Okay, and better than this, I could perturb this map a bit. So if instead I take some F diffeomorphism of the torus that is C1 close to this linear map I had, well, what does that mean to be C1 close? It means not only that points on F, their image is somewhere close to what 2111 would have done to the point, but the derivative is close at every point. So this would tell me that on the torus, at every point, the derivative is something close to this linear map, 2111. So there is a direction, the eigendirections of the derivative are somewhere close by. And so this gives me two invariant line fields given by the eigendirections of the derivative, which now maybe vary slightly, and they're always close to the one that was there before. So now this lives in the tangent space. All right, boop, boop, boop. Okay, so this gives me this kind of picture, and I could integrate these line fields and get invariant foliations, which now are going to be close in the C1 sense to what I had before. All right, and these behave in the same way, because I've cooked them up this way. That one consists of points where if I iterate my map, they get further and further apart, right? The distance between them grows. And the other one consists of points that if under iteration, they approach each other. Okay. And in fact, better than this, sort of classical results of hyperbolic dynamics tell you that, in fact, not only does the picture sort of resemble the original picture after perturbation, but such a map is conjugate by a homeomorphism to the original. Okay. Let's do the continuous time version as opposed to this discrete under iteration, which is the one I want to actually talk about. Okay, so the continuous time version of this picture, here I took a map and I iterated it, is an Anosov flow. And I'm going to talk only about Anosov flows on 3 manifolds. So everything will be on 3 manifold, although this definition generalizes in a sort of obvious way. So an Anosov flow, let's call it phi t. Here my 3 manifold is compact, although it doesn't necessarily have to be, I'll take one that's compact and just has some Riemannian metric on it, is a flow with an invariant splitting. So this is the analog of my eigendirections. Of course, the direction of the flow, the tangent direction of the flow is invariant under the flow. But then I have 2 other invariant one-dimensional distributions called the stable and the unstable one. With the property that one of these is expanded as you flow forward, and the other one is contracted. So more precisely, a way to write this is that, I'll need some constants. There exists some positive constants. So that if I take a vector that's in the stable one, the contracted one, say, and I look at the norm of what happens to it after I flow for time t. So this is a tangent vector, so really I need, I guess, the derivative of the time t map acting on it. And I compare its norm to the original norm of the vector. It gets contracted by a factor that's exponential in t, e to the minus t k v for all t greater than 0. So this is just saying if the size gets contracted in the future, and a slick way to write this about vectors in the unstable is you write exactly the same thing. Now I need an absolute value of t. All right. So if you're in the unstable, you're contracted in the past. Okay, so that's the formal classical definition, but the key take with a picture, or actually the key fact, is that not only do I have sort of one-dimensional invariant distributions that I could integrate and get a picture like this, but if I look at, let's get some better notation here so I don't have to write ddt all the time. Let's call the vector field generated by my flow x. So this is just going to be notation. I'll call this x. If I look at the direct sum of x and the stable, say, these are vectors that are sort of not expanded. Or if I look at this other two-dimensional distribution, these are integrable and thus tangent, or equivalently, to foliations, two-dimensional foliations, called the stable and unstable foliation. And these are characterized by the property that along leaves of the stable foliation, orbits converge, orbits of my flow converge in the future, and on leaves of the unstable, they converge in the past. So a nice picture of this is, let's see, I have a stable leaf here. This is an orbit, and transverse to it, I have an unstable leaf. And so here's a leaf of Fs, here's a leaf of the unstable foliation, and the picture of how orbits behave along these leaves is kind of like this. So you can actually use this picture. One thing that's nice about this is this is a very derivative-y, analytic, almost looking definition. You can use this picture actually as the founding principle and make a definition of a topological Anosov flow, where you say, it's a flow on a three-manifold, so that there's two transverse invariant foliations, and orbits converge in future time along one and do not converge in the past, stay separated in the past. And orbits converge in past and stay separated in the future along the other. And it's this definition that's easy to generalize to a pseudo-Anosov picture where you allow these foliations to have singularities. So one thing I will do in this talk is I will mention the word pseudo-Anosov often, so if this is something you'd like to think about, you can slot it in. But if it's not something that you've ever thought about before, you should kind of ignore this part, and I don't want to overwhelm the audience with definitions. And so there'll be some pseudo-Anosov-y remarks on the side, and feel free to ask if you want more on any of this. But I'll try to sort of keep the essence compact. Okay. Other remarks? So similarly to this, my hand-wavy picture over here, this picture of two transverse two-dimensional foliations for an Anosov flow is also stable under perturbation. If I take another flow that is C1 close to this one, and I do this whole picture and I look at my foliations, they will give me nearby, and in fact a whole conjugate picture of two transverse foliations on my three-manifold. And maybe this is one reason to take these two-dimensional foliations rather than looking at just the one-dimensional tangent foliations to this splitting as the basic object, because in fact these are not stable under perturbation. So this is kind of the topological sort of coarser object to study. Okay. Let's do one example of this, of what is an Anosov flow. UO examples exist. So here's an example. Actually, I already cooked up an example. I can turn my discrete time thing into a continuous time thing by a standard trick called taking the suspension. So this is called the suspension flow. I could take 2 on 1, 1, or I could take my f, like on the previous board. So f should be technically a hyperbolic linear diffeomorphism, not necessarily linear, just diffeomorphism of the torus. So here my 3-manifold is the mapping torus of f. So this is the torus cross the interval. And I glue the two sides together by saying that, x comma 1 is equivalent to, f of x comma 0. So it's, let's get a new board here. So here's my torus. Here's the interval. I use f to glue the back to the front. And my flow, the suspension flow, is just the orbits of it. I say I instruct you to move in a straight line across at unit speed. All right, so phi t of x comma s, say, is what the torus was my first coordinate. Yep, x s plus t. But of course, modulo the gluing. So as soon as I hit the edge, I apply f, and I come back to where I should be on that start. This flow is Anosov. You can check this by hand, provided f has this type of hyperbolicity property where I have eigenvalues, an expanded and a contracted one at each point. This flow is Anosov, and the eigendirections, or the invariant foliations for f, give me my invariant. I just take the product of these. So here I had a contracting one that was looking like this. I just take the product of the product leaves of my previous foliation with the interval. And these give invariant 2-dimensional foliations for the suspension flow. And this is completely believable, just as you check if you believe these are characterized by the property that, say, on this contracting or stable foliation orbits converge in the future. If I take 2 orbits on a common leaf and I apply my straight line flow, well, right now they're completely parallel. But this cartoon on the board is not like isometrically embedded or anything, so you don't need to worry. Let's look at the long-term behavior. I hit here, I apply f. This was the contracted direction, so I end up on another piece of this leaf. But now much closer together because this was the contracting direction for my map. And I continue. Okay, the other classic example, so this is actually a whole family of examples. Family 2 is the classic, and the motivation for the study of these objects in general is that if your 3-manifold is the unit tangent bundle of a surface that has a metric of negative curvature, okay, then the geodesic flow, it has this Anosov property. And your invariant foliations here are the horocyclic foliations for the flow. Okay, but the question I want to address here is, so out of some family of dynamical systems, that includes, geodesic flow and negative curvature, so that's already kind of a fundamental example. I have 3 manifolds with pairs of transverse foliations, and in fact, the leaves of these foliations are further foliated by orbits of the flow. So this is a very rich topological picture. How can we understand the picture to me given by pairs of such stable and unstable foliations in the 3-manifold? Yes, question?
So here you said here you said that if you do a perturbation of the 2-1-1-1 map, then you still get these foliations of the torus that are invariant under the diffeomorphism.
Yeah.
But then later you said that we look at the stable and unstable foliations rather than the stable and unstable directions, because the stable and unstable directions are not
so well behaved. Like if you do a time change of your flow, these will change in a way that's hard to predict. But for instance, if I speed up or slow down the flow, in these two-dimensional distributions, they see the directions orbits head, but not their speed. And so it's sort of a more stable object in that sense. But sorry, I jumped in halfway through your question. Did that?
So I meant to say that in the torus example that you gave, they are somewhat structurally stable. Is that right? Or maybe I'm missing something. Or maybe that's because that's not a flow. That's a different.
Here's the thing. Yes, the one-dimensional distributions here are playing the role of the two-dimensional distributions there.
Okay.
Right. And in fact, if you pass from here, if you try and make this a flow, right, the first return map to this torus of this suspension flow is this diffeomorphism, right? And so this is really the way to turn this into a flow. And here the corresponding objects, well, everything is, take the product with the interval. So
right. Okay. So if the flow was somehow a suspension, then the stable and unstable directions would also somewhat make more sense.
Sure. Other questions anytime are great, especially if you're encountering this picture for the first time. Great. Okay. Okay. So typically, I want to understand what these look like. In the three manifold, the way they look is complicated. Leaves will accumulate on themselves in a terrible and complicated way. In many cases, there are many examples of flows where even the orbits themselves are dense in the three manifold. So that's a messy picture. But we can do this instead of working in the three manifold. I can lift to the universal cover and just remember that there's an action of pi1 that needs to be respected so things descend back down. All right. So the idea here is that this whole thing might be much simpler if I just work equivariantly in the universal cover. Okay. And in fact, it is much simpler. And this is what the following theorem says. That as messy as things might be downstairs, if I lift out these foliations and the foliations by orbit, so upstairs to the universal cover, it's as nice as can be. Okay, so the theorem I'm going to state is, I think, originally due to Verhofsky appearing actually in his thesis using Haefliger's theorem on foliations, where you need to fill in some gap somewhere using a result of Planck. But this is the right era. And I will give an argument, some hand-wavy argument using Novikov's theorem instead, which is what you need to do you need to use actually if you want to do the pseudo-Anosov case, so here's my pseudo-Anosov remark, everything can be generalized using a generalization of Novikov's theorem to laminations of Ghys and Ortel. Okay, but let's do the Anosov version first. So, more people to be credited, but this is I think the original version of this argument. So if I have a compact three manifold, and I have an Anosov flow on it, okay, then many nice things happen in the universal cover. Okay, so one, my manifold is aspherical, so its universal cover is homeomorphic to R3. 2, I can lift my flow. I mean, it just generated by a vector field. Lift up the vector field, you generate a new flow. I'll call that lifted flow, I don't know, phi tilde or something like this. The orbits of the lifted flow are properly embedded lines. So phi downstairs will have many periodic orbits, but they are all represent essential curves in your 3-manifold. So when I lift to the universal cover, I'll get lines. I can lift my invariant foliations to foliations upstairs. So here's 2 invariant foliations for my lifted flow. These have leaves, which are properly embedded planes. Leaves of these 2-dimensional foliations are themselves foliated by orbits of the flow. It is cooked up that way from the beginning. And the foliation induced by orbits on these is as simple as it can be. These are trivially foliated by orbits, meaning that the picture is I have a plane, topologically the picture is I just have a standard foliation like this. I don't have anything like, I don't have any Rabe components. Okay. And finally, 2 such leaves, one of the stable and one of the unstable foliation. If they intersect along one single orbit and not more. So let's stick this. Leaves intersect along one orbit or not at all. Sorry that this is squished at the corner of the board there. So this is clear in my baby example of the suspension flow if you want to think about this in this cartoon. If you look at the universal cover of this, there's 2 directions to unwind, right? There's the interval direction to get R, and there's the torus direction to get R2. And you can see just by hand, right, that now my orbits go in straight lines, my foliations become stacks of planes transverse to one another, and it's sort of R3 foliated in a very basic way, well, in 3 very basic ways. And the magic of this theorem that says that even though that's a kind of very trivial example, that kind of nice behavior is quite common. Well, is basically what you see. Let me okay, I will take a minute just to tell you the kind of key idea of the proof here. Because I think this is really nice, and it's if you know a little foliation theory, it's not bad. Okay, all right. So the first observation is that let's before we lift everything up, let's look what's happening in my 3-manifold, the compact 3-manifold, and the leaves even of my stable, unstable foliation in the 3-manifold are foliated by orbits of the flow. So this restricts their topology, right? I can't have some kind of closed leaf that's a higher genus surface because you can't foliate those, and I have no leaves that are spheres either, right? They have to be like annuli or Mobius bands or just planes or tori or Klein bottles, and that's an exhaustive list. Okay, but better than that, the fact that I have this convergence along stable leaves, so let's look at a stable leaf, means that I cannot have kind of multiple periodic orbits in a leaf. So maybe I had a leaf that was a cylinder with a closed orbit like this, all right? And this is in, I don't know, let's do stable to be concrete to draw pictures, right? This convergence picture tells me that any other leaf on here is going to eventually spiral onto this one. Okay, so in particular, I can't have another closed orbit on this cylinder. All right. So this convergence of orbits tells you that you can formalize this better than I did with my picture, maximum of one periodic, that's just to say it closes up, orbit per leaf. Okay. And better than that, you can't have a torus or a Klein bottle by basically the same argument, thinking about how orbits converge in the future and what this foliation looks like. So this same argument, we also get all leaves in M3 are topologically not properly embedded or anything, planes, annuli, or if things are non-orientable, you might have a Mobius band. So in particular, you have no compact leaves, and your foliations here have no rape components. All right. So you can now use Novikov's theorem, which if you don't know, you would accept this as a black box, and then at lunch you're at a conference on foliation, so you ask your neighbor, what's this thing? And they'll give you a sketch. This tells you that your three-manifold is aspherical, and so the universal cover of it is homeomorphic to R3. And what else does this theorem buy you? The key point is that there's no null homotopic transversal transverse loop to either of these foliations. And then I can even go back to this kind of picture, and it tells me, using again this convergence of orbits, that if I have a closed orbit like this in a cylinder leaf, then that is an essential curve in the fundamental group of my manifold. Because of this convergence property, I can push it off itself and make it transverse. Right. So if ever I have an annulus leaf or a Mobius band leaf, in an annulus / Mobius band leaf, pi1 of the leaf injects into pi1 of the three manifold. Okay, by this conclusion plus this convergence property and this kind of observation, you can push off closed orbit, or you can, the convergence property will give you the existence of one of these closed orbits and the fact that you can find a loop that's transverse that represents the fundamental group. Okay, all right. And the other property, so this is what the kind of thing that this is exactly what you need to do to show that orbits are properly embedded lines. And the leaves, I'm saying their fundamental groups are generated by curves that are essential in fundamental group of the three manifolds. So this is what you use to show that the two-dimensional leaves are properly embedded planes. Okay, so I leave the details. This is not what I want to spend my whole talk on. Fill in the details as an exercise, but these are the essential ingredients that you need to know. The convergence of orbits really restricts the topology of the foliations, and Novikov's theorem buys you the rest. Yes?
Could you conclude that there are leaves on periodic orbit?
Why is there? Yeah. So every closed leaf contains a periodic orbit, again by this convergence type property. So that you need to think a little bit about. Yeah. Min one if well, unless your leaf is a plane, right? Yeah. So here's a fact that's true that I haven't been careful enough to argue, right? Is if so, yeah, on an annulus leaf or Mobius band leaf, there always exists a periodic orbit. Okay, many of your leaves are planes, and so nothing will close. There are no periodic orbits, though. Okay, and I should call this 2'. Other questions? Okay, so that's a hasty sketch proof of what does the picture look like in the three manifold. And now I want to do a trick of reducing dimension. Yes?
How do you say that there is no branching?
Here also it's this orbits converge in forward time property. Yeah. So things are, and not in backwards time. So it's a honest, if you take the derivative type of definition, then it's not, in a picture like this, right, you have the orbits in the same, say, stable leaf that also in, if things are oriented this way or something, also in backwards time they will accumulate, which doesn't happen in this kind of expansive property. Yeah. Okay. Okay, so we've sort of seen the picture here, and now I want to pass from, as advertised, from the three manifold to the plane. Right. And this is a perspective used, it's already sort of hints of this in some of Verhofsky's work and in older papers of Ghys, but it was really promoted and used heavily by Thierry Barbot and Sergio Fenley. Right. So here's something that I can do. I'm going to put a definition inside a theorem. Sorry. So here's a theorem due to Thierry Barbot and Sergio Fenley separately, both around 1994-95. All right. What are we going to do? We're going to take your three manifold, your universal cover with its lifted flow, and the orbits are properly embedded lines. So that's not very interesting. Let's kill them and make each orbit now a point. All right. And hope I don't lose too much information. So I will take the quotient space of this, where I say that each orbit is collapsed to a point. All right. Equivalent to. So I take a quotient by an equivalence relation where on the same orbit, you're now the same. All right. Here's the definition I'm trying to sneak into a theorem. This ends up being called the orbit space. Right? It's the leaf space of the foliation by orbits up here. So let's do some notation for this. O for orbit space of phi. Okay. And the theorem is, what does this look like? All right. Okay, so this is homeomorphic to the plane. All right. All right. And my lifted foliations on the 3 manifold descend to 2 transverse. Now, of course, one-dimensional foliations on the orbit space. Let's call them something, I don't know, that I'll want later, Fs bar, Fu bar. So actually, maybe this is worth saying, not technically part of this theorem, but an observation, right? So observation. Okay. The fundamental group of my 3 manifold acts, of course, on its universal cover by deck transformations. And all the properties of my foliations and my orbits, these were all lifted from downstairs, right? So this action, first it descends this quotient space because it preserves orbits of the lifted flow. Okay. So now I have an action on the orbit space, and it preserves not leaf-wise, but permuting the leaves, preserving these 2 foliations. Okay. So this is the perspective I wanted to advertise. You can pass from the flow to now a plane with some invariant one-dimensional transverse foliations and an action of a discrete group, the fundamental group of your 3 manifold. Okay, let me sketch again. Actually, I think I can do in better detail this time. This result of how you get an actual plane, because it's not so bad. So let's see how this works. Okay. So I want to get R2, so I need some like local charts. So first step is, so I have a flow and I can take a local transversal and hope that this would give me a local chart for the orbit space, right? So I have my flow. Maybe it's going up in this picture in whatever coordinates I chose. I take a disk that's transverse to this. If each orbit passing through this disk is really a distinct orbit, then this is injectively immersed into my orbit space, right? This was nicely done, and that will give me a local chart. So this gives local charts, provided that if I take a small enough little transverse disk, no orbit of this lifted flow intersects it twice. Okay, so what's the enemy if this is not in a nice injective chart, but say this orbit hits it here, goes around somewhere and comes back in another spot. I don't know, let's draw the spot far away to make it clear to people at the back. Okay, so I need to show that this doesn't happen. Why does this not happen? Well, if it did, then what's this transversal? Let's draw where my, say, stable and unstable foliations are. I'm in 2 different spots. So either I'm on a different stable leaf or on a different local unstable leaf. So let me draw it in red on this one, up to switching red and blue, or maybe even for both. I'm on different, so these are slices of my 2-dimensional foliations that go through here. I'm on at least different local stable leaves. Or I guess I'm drawing them in red, these are unstable. Some of these will differ. And so what I can do is I can use this to slightly push off this orbit off itself in a way that will eventually connect back up, but is always transverse to the whichever one I've drawn here, the unstable foliation. All right, so if you met it in two different spots, you could say, I'm going to push gradually as I go around backwards, I'm going to push, or as I go around forward, I'm going to push more and more to kind of this, what was I doing, to the left. So I'll start off this way, come around this way, and be able to make a closed loop that's everywhere transverse to one of my foliations. Okay. So, but if it did, you could produce transverse loop to the lifted Fs or Fu, which is not going to happen because these are nice foliations by properly embedded planes. Novikov's theorem does not let you do this. Okay. So contradiction. Okay, so I have local charts. This is good. It means that I guess at least it's a two-manifold, but maybe not Hausdorff. Maybe not simply connected. There's lots of things to check. Oh. Okay, so the fact that I get something, that was my step one. Connected, here's other properties of R2 you need, right? The fact that I get something, this orbit space, this quotient space, is connected, well, it's a quotient of a connected space by an equivalence relation. That's great. And simply connected, and that's also an elementary topology exercise that I've taken these properly embedded lines and collapsed them to points so I get something simply connected. And so now I have a two-manifold that's connected and simply connected, and if it was Hausdorff, I would be the plane. So I need to make this kind of argument. And the idea here to show that it's Hausdorff is I'm going to use the fact that I have these two other foliations when leaves meet along the foliation by orbits. Okay. So what do I need to do? You give me 2 points in this quotient space, so 2 orbits. So given 2 orbits, I don't know, alpha, beta orbits. All right. If they happen to live on the same stable or unstable leaf, I'm happy because of this assertion that leaves are trivially foliated by orbits. So what does that mean? Another orbit will sit in between them, and the unstable leaf, or the stable leaf, whichever one I wasn't looking at right then, will meet this transversely and separate the two. Right. So if on same F, S, tilde or F, U, tilde leaf, all right, maybe I'll draw a picture in the quotient space to make this look better. I have this leaf, which is a plane, and I've collapsed every one of these orbits at a trivial foliation to a point, so I get a line. I have my 2 orbits, which are in different spots. So I can take some point that's in between them on the line, look at the other leaf, stable or unstable through it, and have a line that will divide this into 2 disjoint open sets, so I'm happy I have different neighborhoods. Okay. So these can be now separated by F U slash F S leaf. Okay. If they're on different, what do we need here? So case 2, if on different, say, FU leaves, well, there's two things that could happen. Either I might win right away in the unstable leaf space. There might be an unstable leaf that separates these two leaves, right? So maybe alpha is over here, beta is on something over here. And in fact, there's a whole leaf that divides my 3-manifold into 2 disjoint open sets, which collapse the disjoint open sets in the leaves in the quotient. It's good. So if on different separated in, say, the unstable leaf space, then again we win. Right. Or else what I might see is something that, let me draw a 1-dimension down picture as a heuristic. Alpha lives on some leaf, beta lives on another, but I have a sequence of unstable leaves that accumulates simultaneously to both. Could happen. All right, so now what I need is to somehow find a different argument to separate these into open sets. All right. Well, I'm going to now use a stable leaf to do it. All right. So consider along the leaf of alpha some stable leaf that meets it on the side of beta. What am I saying by side? I should actually compare in nearby limiting leaves. This will intersect there. If I made the bad choice and I was over there, I should be on this side. So I'll look at some transverse stable leaf, and I claim I can use this to separate the two. Okay, what would be wrong, what would be bad is if instead this leaf intersected it twice. That's the only problem I have to worry about. Sorry, not intersected it twice. I'm already ahead in my logic. If this leaf intersects there, I would have a problem. I haven't divided it into 2 open sets. Okay. But that's not allowed to happen. If I saw a point of intersection on both of these non-separated leaves, then on one of these nearby accumulating ones, I would see a leaf of the stable foliation that intersects it twice. Right? And that's forbidden by the big theorem on the structure of these foliations in the universal cover. Right. So this behavior cannot happen. Which tells me that the real picture, I don't know, I'll draw it in yellow, is that if I take a lifted stable leaf, it divides the 3-manifold into 2 pieces that separates these 2 orbits, giving me the Hausdorff property I wanted. Okay. So to write a sentence, if non-separated, we're going to use the fact that Fs, Fu leaves, a pair meet at most once. Most along a single orbit to separate these by a stable leaf. Those are all the cases I had to consider. Now I have this nice Hausdorff simply connected 2-dimensional manifold. It's R2. Now that I know that it's R2, actually, what else do I have to show? I descend to transverse 1-dimensional foliations, this last assertion, and that comes exactly from my local charts, right? It's already cooked up. My local charts are local transversals, and then a local transversal to my flow, I see 2 transverse foliations, the stable and the unstable one. So that comes for free once you know how to make charts. Okay. Yes.
And it's not compact.
So it's not the sphere because it's foliated?
Yes, sorry. It's also, yes, it's foliated, so it's not the sphere. Good. Did I miss anything else? Someone else should be keeping track. Good. Or it's a quotient of R2 by lines. That should give it 2, 2. Okay, so let me conclude. I'm going to steal another half minute in exchange for the lovely SMF video, and to set us up for where we are going to go next time, which is any board is fine. We'll bring this one down. Yep. Which is a statement that this, understanding this action of this discrete group on this foliated plane is all you need to know. If you want to reconstruct the entire three-dimensional picture that I was drawing there. So this is a theorem of Barbot, which is the starting point for the whole perspective I want to present in this mini course. It's the following. I'm given some three-manifold with an Anosov flow. Let me state it this way. I want to say the orbit space picture determines the flow. So I'll say that if you have two flows, okay, these flows are the same if and only if these pictures are conjugate. More precisely, same in what sense, there exists a homeomorphism of the three-manifold taking orbits of phi to orbits of psi. And since my two-dimensional leaves are characterized by orbits, the sets of orbits that converge in forward or in backward time, automatically this says hence taking leaves of the stable or unstable for phi to respectively the leaves of the stable or the unstable for psi. Right. This happens if and only if there's a homeomorphism of the plane. Maybe I'll call this, I don't know, this one should have a name. Let's call it H. I'll call this one suggestively, I don't know, like H bar or something. From the orbit space of phi to the orbit space of psi. Okay. So these are foliated planes. That is equivariant with respect to the action of the fundamental group. So more precisely, on this equivariance point, it says that if I apply some deck transformation, gamma, from pi 1, okay, to a point, I don't know, x in the orbit space, and then I apply h bar, this is the same thing as if I did h bar and then gamma, except I need an identification of how pi 1 acts on the orbit space. For instance, if you're going this way, if you start with one of these homeomorphisms, if it's not isotopic to the identity, there's going to be some weird identification, well, coming from the isotopy class of S, of pi 1 of the three-manifold acting here to pi 1 acting there. So there'll be some automorphism, I don't know, rho, of pi 1 that you have to take into consideration, where this is induced by H. Go in the opposite direction. If you have an equivariance like this, then you arrive at a homeomorphism that induces this exact automorphism of pi 1. Okay, so what's the upshot here? a flow and its orbits are determined by the conjugacy class of the action of pi1 on the orbit space. So anything I want to know about the flow should be visible here. For instance, like, does there exist a closed, anything topological, right? This is not sensitive to time change. It's like, how do the orbits behave? So you want to answer a question about the flow, like, does there exist a closed surface in the three-manifold transverse to the flow? Okay, that's a statement that you should be able to say in the language of an action of a group on a bifoliated plane. Right. You know, I don't know, are there infinitely many distinct periodic orbits in the same free homotopy class? That's a topological statement that should correspond to something you can say about a group acting on the plane. Okay, so where we're going next, I will end now, is that starting next time, we will forget the three-manifold picture, and we'll study, like, very abstractly the idea of groups acting on planes with two-dimensional transverse foliations, because this is a rich class of dynamical systems, and one that, if you do this problem of translation correctly, will teach you anything you want to know about Anosov flows. Okay, thank you.
Questions, but in order to get your questions recorded, please give me a few seconds so that I can give you the microphone.
Maybe just a comment. As on the picture of the conference, there is a picture of André Haefliger.
Yes.
So you can substitute the use of Novikov's theorem by one small part of it, which is Novikov's theorem. I don't know people knowing the proof. Maybe in this audience, maybe there is one person knowing the proof, but two, I don't know. But I don't know the proof of Novikov's theorem. But one small part is a result by André Haefliger, which says that if you have a codimension 1 foliation on the homotopic to zero transverse curve, then you have some curve on a leaf having trivial autonomy on the one side and non-trivial autonomy on the other side. As another flow don't have this kind of curves, you immediately know that you don't have transverse homotopic to zero curve. And then you can go directly to the theorem of Barbot Fenley, just changing a little bit is the end proof, but really slightly, and no more complicated, and you just can switch the part of Novikov's theorem.
Yeah, that's super nice. Actually, the only reason I present it this way is because I have this mission, which I'm quickly abandoning for lack of time, to give some hints at how you might treat pseudo-Anosov flows, because a lot of people care about these, and I do not know how to get that. We need to somehow generalize Haefliger to singular foliations of bad regularity. So, but that's, yes, that's the correct argument, and already somewhat the strategy taken by Verhofsky to do this too. Yeah. Okay.
More questions? Well, if not, let's thank Katie again.
Okay.